In this video, we will continue building the movement states for our citizens. In order to finish the wander state, we need to introduce collision handling into our map system. We are going to implement a method called isPassable, which will take two arguments. The first is an int2 vector representing the starting position, and the second is a direction we want to travel on the map from that starting position. We are also going to associate vectors with each direction by defining a dictionary in our map info class. Right now, we simply have abstract directions associated with the possibilities on our map, but to actually calculate movement, we will need the vectors associated with each direction. Let's open up the class and define a new static dictionary which uses the direction enum for its key and has int2 vectors for its values. We will name it direction vectors. Now we just need to associate each direction value with a vector in the dictionary. Let's take a look at our map to understand how the coordinates are laid out. We will return true from the isPassable method just to clear up this error for now. If we zoom in on the origin of our map, we can use these overlays as guides to help us figure out the direction vectors. This direction going towards the orange overlay is north. In terms of a vector, that will be 0, 1. To move north from the origin, we would move 0 tiles in the x direction and 1 tile in the positive y direction. The direction going towards the purple overlay is east. Its vector would be 1, 0. To move east from the origin, we would move 1 tile in the positive x direction and 0 tiles in the y direction. Let's go back to the map info class and define all of our direction vectors now. You can see we've already started by defining the east direction as 1, 0. We will now follow this same pattern to add the rest of the directions. We're going to add plus signs to each of our positive numbers just so everything lines up nicely. Now that we have these vectors available, we can continue building the isPassable method in our map system. We will start by defining a vector that represents the end position where we are trying to move the citizen. We can calculate this by taking our start position vector and adding the vector associated with the direction that was passed into the method. The first thing we will check is whether the end position is solid. If this is true, then this path is definitely not passable and we can return false right away. If the end position is clear, then it gets a little bit more complicated. We first need to check if we're moving in a cardinal direction. This is either east, north, west, or south. We will define a local Boolean variable that checks to see if the direction argument is any of these cardinal directions. If this is a cardinal move, then we can return true. We know the end position is clear because we've already made it past the first if statement, so there is nothing standing in the way of this move. But now we need to deal with the case where the citizen is trying to move in a diagonal direction. The problem is that we do not want our citizens to be able to cut corners, so we'll have to check the surrounding tiles they might run into while moving. Let's return false at the bottom of the method just so we can run the application without errors and take a look at the map again. If we zoom in on this wall, we can get a sense of the problem. If the citizen is sitting on this tile and they want to move in a cardinal direction, they're going to be all clear because none of those tiles are solid. But if a citizen is sitting on this tile just to the south of the wall, they will actually run into the wall if they try to move northwest. In this case, we actually have to check 3 tiles to make sure the path is clear. We first check the end position, which is the northwest tile, but then we also have to check the north tile and the west tile to make sure they are also not solid. Now we can go back and finish the isPassable method by accounting for these diagonal movements. Let's delete the return false statement, and now we're going to define a few local variables because we're not sure ahead of time which tiles we'll have to check. We will define one Boolean variable for each cardinal direction. Now we can create an if statement that checks to see which direction we're trying to travel, and this will allow us to decide which tiles we have to check in order to confirm it's a clear path. For instance, if the citizen is trying to travel northeast, then we will have to check that north is passable and east is passable, so we'll return true only if both of those variables are also true. The other diagonal directions will follow the exact same pattern. Remember, we've already taken the cardinal directions into account at the beginning of the method. That almost completes our method. Even though we know that this exhausts every possibility, the editor is not convinced because there could have been something else like a null value passed in as our direction argument. So we need to include one more return statement at the bottom to handle this situation. If we make it all the way to the bottom, we will simply return false to be safe. That completes the isPassable method. We can now make use of this method to complete our WanderMovementState class. We will use the Simulation Manager Singleton instance in order to get access to the map system where this method resides. We will pass in the citizen's position vector as the starting position argument, and then we will pass in the new direction we are attempting to move as the direction argument. Now we can deal with the case where the citizen is free to move in the new direction. We are going to extend our MapInfo class in order to handle this case. We want the citizen to take a longer time to move in a diagonal direction. Therefore, we want to give them a larger cooldown if they move in a diagonal direction. We are basically going to use the Pythagorean theorem to define the cost of moving in each direction, and then we'll store these costs in another dictionary in the MapInfo class. We are going to say that it costs the citizen 10 ticks to move in a cardinal direction, east, north, west, or south. If we think of a triangle that is 10 units long at each base, then the hypotenuse would be roughly 14 units long. This corresponds to moving in a diagonal direction on our map. Let's return to our MapInfo class and define these costs for each direction. We will start by defining a new static dictionary that will use a direction type as its key and an int as its value. We will name this dictionary Direction Costs. We will copy the initialization from the Direction Vectors dictionary to avoid retyping all of the directions. Then we will set each cardinal direction to 10 and each diagonal direction to 14 to match our triangle calculation. Now we can return to the WanderState script and use this new dictionary to set the cooldown for our citizen. We will look up the correct value by giving the new direction as a key. We will then assign this new direction to the citizen's direction property to update their direction within the simulation. We're actually going to change the citizen's direction even if they are not able to move, so let's lift this line up out of the if statement. Now we'll return to the if statement and update the citizen's position based on the direction they're trying to travel. We know their path is clear, so we'll use the Direction Vectors dictionary to update their position by adding it to their current position just like we did in the isPassable method. The last thing we'll do is call the updateRenderPosition method on our citizen, so that the citizen can fire the event that will request an update to their rendered position. Remember, this method calls invoke on the event handler back in our citizen class, and soon we'll subscribe to these methods in the world render component so that we can actually update the rendering of the citizen based on its new values. Now, let's complete the else clause in the WanderState's tick method. In this case, the citizen has chosen a new direction, but it is not able to actually move in that direction. We will treat this situation very similar to how we wrote the idle state logic. We will set a short cooldown value for the citizen, and then we will simply call the updateRenderDirection method on the citizen. Remember, we've changed the direction up at the top above the if statement. This completes the WanderState logic. We now have both of our movement states fully implemented. Let's return to the citizen class and include a new variable that allows the citizen to hold a reference to its current movement state. We have instances of each movement state stored in this movement states dictionary. We can now define a private variable of the type citizen movement state in our citizen class. This is the abstract base class for all of our movement states, so we can assign any of our movement states to this variable. Let's start out by assigning the idle state to this variable at the bottom of the constructor. We look up this state in the dictionary using the movement state type as a key. Now let's move to the citizen class, and right after we decrease the cooldown value for the citizen in the tick method, let's call the tick method on our current movement state. We now have a basic state machine implemented for our citizen's movement state. If we run the application now, we will not see any changes in the rendering of our citizens. This is because it is only in the simulation logic that their properties are being updated. If you want to test this out, you can output the cooldown and direction values and watch as they get reset to random values every time a citizen acts. In the next video, we will define responses to these render update methods that we are firing whenever the two methods at the bottom of this class are called. This way, we'll be able to update the rendering of our citizens based on their new properties. This will allow us to finally see the movement states in action.